All right, so we're in the PowerPoint for the Chinese mathematics, looking at this screen, looking at the slide about the area of a circle in the 9 chapters on the mathematical art. So I'm going to look at the third one, and this is area of a circle. And it says the rule is that the area of the circle is the diameter multiplied by itself, then multiply the result by 3, and then divide by 4. Okay, so think about when you might use that rule. I might use that rule for finding the area of a circle if I only know its diameter. If I know its diameter, this is what's going to work. I don't know its circumference. I don't know how far around it is. So this is the one that I would use if I know the diameter of my circle. All right, let's solve it like we've been doing before and figure out what they're doing with pi. We know the area of a circle is pi r squared. So set up pi r squared is equal to the diameter multiplied by itself, so d squared, then multiply that result by 3 and divide by 4. Okay. Well, that's fine, except on the left-hand side, I've got the radius, and on the right-hand side, I've got the diameter. So let's write in terms of one of these. Let's change that diameter and let d equal 2r. The diameter is twice the radius. So I've got pi r squared equals 3 times 2r squared over 4, or 3 times 4r squared over 4. And when I simplify this fraction on the right side, I can divide the numerator and the denominator by 4, and I get 3r squared. So I've got pi r squared equals 3r squared. And if I divide both sides by pi, my approximation is pi equals 3. Well, that's not the greatest approximation in the world. You know, it's good for, what was the saying? It's good for horseshoes and hand grenades. But, you know, if I needed to be really precise, I might want to use a different formula. I would really like to have a better approximation. The ancient Greeks got closer to pi than the ancient Chinese at this time. Okay, so besides just thinking about what the Chinese are doing, also kind of keep in your head about what's going on in some of these other civilizations at this very same time. Okay, so let's go back over here. Close only matters in horseshoes and hand grenades. There you go. Oh, no quizzes. Share the screen. Where am I? This one. Okay, so let's go to the next one. Can y'all see that okay? Nobody's saying, okay. All right, in chapter 4, they show you the procedure that they use for finding the square root of a number. And of course, it would be a big number, smaller numbers, you know, it's not that big a deal. But we're going to find the square root of 182,329. So let me write that down before I forget the number. The square root of 182,329. And this was in chapter 4 of that book, 9 chapters on the mathematical art. All right, let me show you how they would do this. It's a cool method. It's just going to take us a little while to do it. It certainly isn't as quick as if we could just grab our calculator and punch a couple of buttons. All right, now, remember the problem said determine the side of a square of an area 182,329. It's geometric. So this idea of the connection between the geometry and the algebra again, I'm not just finding the square root of a number, I'm finding the length of a side of a square whose area is that number right there. All right, so keep that in mind. Now, my first question is, how big is the number? How big is the number that we're looking for? And I'm going to write up here, S is equal to that square root. Okay. I need to know this because in the procedure for finding the square root, I'm going to find one digit at a time. So if S is a one-digit number, then S is between 1 and 10, including 1. S is greater than or equal to 1, but it's less than 10. And if that's the case, then if I square all of these numbers, 1 has to be less than S squared. 1 is less than or equal to S squared, which is less than 100. Well, that's not big enough because S squared is way bigger than 100, so it's certainly not a one-digit number. All right, that seems obvious. What about a two-digit number? Well, if it's a two-digit number, then we've got 10. S is between 10 and 100, not including 100. And then what's going on with S squared? Well, S squared would be bigger than or equal to 100 and less than 10,000. All right, we're looking for 182,000. It's bigger than that one. We got to keep going. It's not a two-digit number. What about a three-digit number? Well, S will be between 100 and 1,000, strictly less than 1,000. And that means that S squared will be between 10,000 and 1,000,000. Well, 182,000 is between those two numbers. So I know that S has to be a three-digit number. This is it. And that's important. S is a three-digit number. And if I let those three digits be A, B, and C, I would think about how I would write it like A is in the first place, B is in the second place, C is in the third place. And in our notation, let's write this in expanded notation. That means that S is A times 100 plus B times 10 plus C. So this procedure helps us find the square root of the number by finding the digits one at a time, starting with the biggest digit. All right, well, let's draw a picture here. I want a square. See, how long was that? 2 1/4. Here's a pretty good square. Now the area of this square is 182,329 square units, whatever the units are that we're talking about. S is the length of each side. Remember, S is equal to that expression right there. And what I'm going to do is divide up the sides into those three parts. So if S is this is how many hundreds I've got. This is how many tens I've got, and this is how many ones I've got. So this is 100A. That length right there is my hundreds. This length is my tens. This length is my C's. And I'm going to do the same thing over here. So this is 100A, this is 10B, and this is C. And what I want to do is draw in these lines to separate this square into several pieces. All right, let me draw this line straight across, this one straight down, straight down, straight across. Okay. So I've got it in 9 pieces. They're not all the same size. Some of them are, but not all of them. Now, the only piece that involves A, that involves that first digit, is this big square up here in the corner. The area of this big square is 100A squared, which is 10,000 A squared. Okay, well, that's only part of the area. So the area of this square is less than the area of the entire square. So I could say that 10,000 A squared is less than 182,329. And I know for sure that I don't have to put less than or equal to, because whatever A is, this number is going to end in a 0 and this one's not. So I feel good. I'm okay using that less than sign. And let me just make a note over here. What we're doing is finding A. Well, I'm trying to solve for A. So let me divide both sides by 10,000. A squared is less than equal to, divide by 10,000. I get 18.2329. Now, what I want to find is the largest value for A that's going to make this inequality true. I want to take out the biggest chunk possible out of my square. So that means I need to find A as big as possible. So make a note to find the largest A for which the inequality is true. Okay. So if I think about it, if A is 1, I mean, I know what it is. I don't really have to go very far. If A is 1, 1 is less than 18. Yeah, but could I get bigger? Oh, I could jump all the way to 6. 6 squared is 36. Oh, that's too big. 5 squared is 25. That's too big. 4 squared is 16. Oh, I knew that. 4 squared is 16, and that is the largest square number under 18. So A must be 4. So I've got one of my digits so far. I know that the square root of this number, that number right there, is 400 and something. I just don't know the tens and the ones. So I'm going to go back up here to my picture, and I know that's going to be 400. I know that's 400. So that turns out to be 160,000 is the area of that square. which means what's left over, this kind of backwards L-shaped piece, this piece has an area of 182,329 minus 160,000, which is equal to 22,329. So I've got to distribute 22,329 across those 8 pieces. And by the way, this shape appears an awful lot. We're going to see it again in some other problems we do. This kind of a backward block L is called a gnomon, G-N-O-M-O-N. I've seen that in crossword puzzles. And I wouldn't know it. Actually, I think I've seen that word on Jeopardy. I've seen them. That was the answer to one of the clues. All right, well, now we know what A is. Now let's figure out what B is. And I'm going to go to the next page because I'm almost out of room. So I need to find B. And I need to refer back to my picture. So I'm going to kind of go back and forth. The part of the picture that involves B is this right here. Okay. Because this rectangle has an area of 400 times 10B. Which is 4,000B. This rectangle has the very same area. It's 10B times 400. So its area is 4,000B. This rectangle has area 10B times 10B. So its area is 100B squared. Okay. So I want to set up another inequality that involves B, because I'm going to solve for B. I know the area of these 3 pieces has to be less than 22,329. There's my inequality. So I've got 4,000B plus, need another 0 in there, plus 4,000B plus 100B squared has to be less than 22,329. And again, I know that I'm good with the less than sign because that number is going to end in 0. That one will, and that one will. So this number is not going to be the same as that one. I can easily say less than. All right, add those together. I've got 8,000B plus 100B squared is less than 22,329. So I'm going to divide everything by 100 and I'll get 80B plus B squared is less than 223.29. All right, you could use your calculator if you needed to, but I think we can estimate and figure this out. If B is 1, 80 plus 1 is 81. Yep, that's less than it. But is that the biggest one? Try 2. B is 2, that's 160 plus 4. Okay, that's still less than that. What about B equals 3? Well, 80 times 3 is 240. I'm already too big. Okay, it's not 3. It's got to be 2. B must be 2. That's the largest value for B that makes that inequality true. So now we know that A equals 4 and B equals 2. And our last thing to do is figure out what's the ones digit. So what's C? If I go back over here to my picture, the part of this gnomon is getting a little bit smaller. This gnomon is that outside piece, and it's 2 rectangles and a little square down here in this corner. Well, the square in the corner has an area of C squared. 10B, we knew B was 2, so this is 20. This is 20. So this rectangle is 420 times C for its area, 420C. Same thing for this rectangle, and I'm talking about from here to here, and from here to here. This area is 420C. Oh, well, wait a minute. I need to do one more thing, because what's the area? I'm not quite ready to write my inequality yet. Well, I can start though. The area of this piece is 420C plus 420C plus C squared is less than or equal to what? Okay, that's what I need to figure out. So if I go back over here, the green part is that white square and the yellow pieces, which turns out to be one big square, 420 by 420. And I do have a calculator. So 420 times 120 is 176,400. So the area of the green part is 182,329 minus 176,400 oh shoot, which I should have just done this, is 9, 2, 9, 11, 5, which is 5,929. So come back over here to find C. That's the number I need in my inequality, 5,929. So 420 times 420 is 840C plus C squared is less than or equal to 5,929. All right, well now just to make this go a little bit faster, if these are equal, this C squared, this number ends in a 0. C squared is going to have to end in a 9 so that these are equal, which means C is either 3 or 7. So if C is 3, I'd get 24, 25, 20 plus 9. That's not going to be big enough. But if C is 7, 840 times 7 plus 49 gives me 5,929. So if C equals 7, we get 5,929 is sure enough less than or equal to 5,929. And there's my ones digit. So the length of the side of the square is 427, whatever units I'm using to measure the length. Remember, this is before the days of calculators. So when they need to find the square root of a big number, they need some way to figure out what it is rather than just trial and error. They need some kind of an algorithm that will tell them how to find the square root of any number. Also remember, when they're doing all of this, and look at this combination of geometry and arithmetic and algebra, they're using those old numeration systems. They don't have algebra. They don't have variables. They don't have exponents, parentheses, equal signs. I mean, just imagine how difficult it must have been just to understand the problem and figure out how to write it down when you don't have all of that, those symbols that you need, which explains why symbols in mathematics were so important and why once we've got the symbols, math just explodes. I mean, it changes so quickly once we've got symbols that we can use in algebra and geometry and the other areas of mathematics. Okay, that's pretty cool. When I was in high school, we didn't have calculators, and I mean, this wasn't in the day when I had to walk to school in the snow, but what am I trying to do here? I need to stop this. I need to stop talking and do this. And so when I was in high school, we learned methods for finding the square roots of really big numbers. I don't remember how we did it. I do remember we did it one digit at a time, and we'd find the biggest digit first. And it might have been something like this. I don't think it was exactly this, but it was similar. So that was pretty cool. I mean, you know, it was before the day of this, when it took 2 seconds to figure out what your answer was. All right, I need to watch the time. Okay, so let's go over to the next. Did I share the screen? I don't think so. Where am I? Right here. Okay, so here we are. Chapter 9, remember, was the last chapter of the book, and it was about right-angled triangles. So I know when I set up this problem, I'm going to have some right triangles in it. So let me read the problem first, and then I'll have to maybe go back and forth between my paper and the picture. Let me write over here what we're doing. This is chapter 9, the pond problem. Now, one of the most difficult things that we have seen about these ancient problems is not that once we get them set up, it's difficult to solve them. Usually we can get a pretty easy equation and we can solve it pretty easily. It's figuring out what the equation is supposed to be, because lots of times they leave out information and assume that we understand something about the problem that, you know, we know today. Don't assume anything, but back in the day, they did make some assumptions. Here's one of them. Given a square pond with side 10 feet. Okay, so think about what this is going to look like. You've got a pond, and if you looked at it from the top, it would be square. 10 feet on each side. That square pond goes down into the earth, straight down. I don't know how far. In the very middle of the pond, there's a reed, a bamboo stick is coming out of the very middle of the pond, and it sticks out about 1 foot. It sticks out 1 foot above the water. All right, now here's the thing. I'm going to stop sharing here for a minute. If I stand on the edge of the pond and I reach over and grab the top of the bamboo stick, I'm going to pull it over towards me. Bamboo's really stiff, remember. I'm going to pull it towards me, and as I pull it towards me, it's going to go down, you know. It's real tall up here, but as it comes down this way, it's coming down. And it's going to come down until the top of it is right at my feet at the edge of the pond. The top of the stick is at the edge of the pond. That's the picture we need to draw, okay? Let's draw that picture. Okay, I'm looking at this pond from the side. So imagine you dig down in the earth. You're like, I don't know, a groundhog, and you dig down into the earth next to it, and you're going to look sideways, and you see this pond. It's got a flat top, And if we could see the top of it, we would know it's a square. But I know that that top is 10 feet. That was given to me in the problem. That's the length of the side of this square top. All right, there's the top. It's 10 feet by 10 feet. So that right there is 10 feet. Okay. What I don't know is how deep the pond is. So I don't know that right there. I'm going to call it D. Now, the other thing I know is that I've got this stick sticking up right here so that it's the top of it is 1 foot above the water line. So that right there is 1. And when I'm standing right here on the edge of the pond, I'm going to pull this over. So it's going to come that way. And when I pull it over and pull it all the way to the edge of the pond, this is where that bamboo stick is going to end up. So that's the bamboo stick, and the top of it is at the edge of the pond. Now, this bamboo stick was straight in the middle of the pond, so it made a right angle with the top of the pond. I see a right triangle. I see 2 right triangles. I could work with either one of them. This right triangle here that has the solid lines, this is half of the base. And if I know that that base has length 10, then of course, this right here has length 5. I don't know what this side is. I'm calling it D. I don't know what the length of the stick was, but I do know that it's 1 unit longer than the side. So I can write it as D plus 1. Oh, I've got a right triangle. I've got the lengths of 3 sides. I've got 1 variable. It's screaming Pythagorean theorem. So using the Pythagorean theorem, I've got D plus 1 squared. The hypotenuse squared is equal to 5 squared plus D squared, the sum of the squares of the leg lengths. So let's solve this equation. I've got D squared plus 2D plus 1 equals 25 plus D squared. Subtract D squared from both sides. Subtract 1 from both sides, and I'll have 2D equals 24. And then divide both sides by 2. D has to be 12. So the depth of the pond is 12. D plus 1 is 13, and that's the length of the reed. Okay, now let's go back over to what they've got in the book. Y'all stop me if I'm going too fast. This is really strange talking to this screen. I don't see any faces. Nobody's there, and I can't hear anything. So I'm assuming that you haven't all gone to the kitchen to make a sandwich. All right, so let me come back over here and go to here. All right, I want you to look at how they solved it, because in the book, you've got the statement of the problem, and then you've got written in words how they solved the problem. So how they solved it is just as interesting as the problem itself. The rule is to multiply half of the side of the pond by itself. Okay, I'm going to write that over here and then kind of come back to it. So half the side of the pond, that's S over 2, and I'm going to square it. decrease this by the product of the length of the reed above the water with itself. All right, I'm going to generalize this and I'm going to say, let's suppose problems like this, you know, we knew this length was 1. Suppose we don't know it. Suppose we just know it's L. So decrease it by the length, by the product of the length of the reed by itself. So decrease means subtract. L squared, where L is the length of the reed above the water. Divide the difference by twice the length of the reed above the water. So divide that by 2L. And this gives the depth. Add this to the length of the reed above the water, and that will give you the length of the reed. All right, let's go back over here. Stop sharing. All right, so when I algebratized that, this is what my equation looks like. S over 2 squared minus L squared equals 2L over 2L equals D. All right, look down here. Suppose I set this up in the same way so that this is D. 5, I'm going to generalize this again. This is D, this is S over 2, and this is D plus L. So using the Pythagorean theorem, I've got D plus L squared equals D squared plus S over 2 squared. Multiply this out, D squared plus 2DL plus L squared equals D squared plus S over 2 squared. I can subtract D squared from both sides. Now, what am I solving for? I'm solving for D. So 2DL equals S over 2 squared minus L squared. Divide both sides by 2D. That's exactly what I got. I'm solving for D, not L. So this needs to be D, and this needs to be L. Now, I got the same thing when I interpreted that Chinese rule. It's really interesting that the rule that they gave was generalized. They didn't have a way of representing the side as D and the length above the water as L, but they were able in words to tell you how you would solve problems like this in general. But here's the deal. The problem is stated in a very specific way. You know exactly how deep the pond, you know the side of the pond, its length. You know how far above the water the reed sticks. But the rule is general. I think that's amazing that they were still thinking about, well, but what about all problems of this type where this is what's given and this is what's not given? Pretty cool. Okay. So let's go on over here. Now, given a city, this is again chapter 9, so I know it's going to be right triangles. Given a city to be measured, it has gates opening in the middle of the sides. 30 bu from the north gate, there is a tree. At 750 bu from the west gate, one can see the tree. All right, now again, we're going to have to make some assumptions about this problem. And one of them is that this city is square. And I know we have to decide that because the first time I solved this, I thought I'd be really clever and say, well, you know, maybe it's not square. What if it's a rectangle? And then what? And oh gosh, it was just a mess. So I went back and said, yeah, you know, they really meant for everything to be a square. So I've got, all right, I've got the numbers. So let me go over here, stop sharing. I'm not going to be quite as particular here. Here's my city problem. And oh, I thought here's a square. Oh, I don't know if I want it that big. Okay. Now I know that in the center of each side, there is a gate. It tells me that 30 bu, which is the unit of measure, 30 bu from this north gate, and I'm going to set this up so that this is north, south, east, and west. 30 bu from that gate is the tree. You can tell us it's on the outside of the wall. Of course it is. Doesn't work if it's not. So the tree, if I walk 30 bu up this way, this is 30. There's my tree. Okay. And then I'm walking out the west gate. So I'm walking over here. And as I walk, I look over my shoulder, look back this way. Well, when I'm right here and I look back over my shoulder, I'm not going to see anything but the wall of the city. When I'm right here, I don't see anything but the wall of the city. I can't see past that corner to see the tree. So the first time I can see that tree is when my eye is lined up with the corner of that building. Okay. And I'm gonna, oh, this is not drawn to scale at all. Okay. So that happened when I was 750 bu going out the right west gate. This really needs to be 25 times as long as that, but that's not going to happen on this size piece of paper. But that's the setup. Okay, right triangles. There's a right triangle. I went due north. Here's a right triangle. I went due west. Now, what do I know? I don't know the length of each side of the city. Suppose I let that be S. Well, the gates are in the middle of the walls. So this is S over 2, and this is S over 2. That length is 30, that length is 750. Okay. I have to tell you, I am so trained to Pythagorean theorems, to problems that use the Pythagorean theorem, that the first time I solved this, I drew in this right triangle and tried to set up a Pythagorean relationship, but I didn't know the length of that side. So I wrote it as the length of this side of this little triangle plus, it was a mess. It's so much easier to look at it a different way. Not as the Pythagorean theorem kind of problem where I've got the relationships of three sides. I don't have the relationship between three sides of the triangle like I did in that last problem. I have two triangles and I know two sides in this one and two sides in this one. All right, now think about those two triangles. This line right here is parallel to that side of the city. Those are parallel lines. That line of sight is a transversal, which means I've got corresponding parts here. So those two angles are the same measure. So two angles of this triangle are the same measure as two angles of this one, which means the third ones have to be the same. That's the same as that one, which means I've got similar triangles. And the absolutely wonderful thing about similar triangles is that I've got sides that are proportional. As long as I've got corresponding sides. And look, I do. I've got short leg to long leg, short leg to long leg. So let's set up that ratio, short leg to long leg for each of these triangles. So this is 30 over S over 2. and that's equal to S over 2 over 750. And when I solve this equation and multiply both sides by 750, both sides by S over 2, I get 30 times 750 equals S over 2 squared, which is S squared over 4. Solving for S, so I'm going to write this as S squared equals 4 times 30 times, all right, I'm not going to use my, grab my calculator. I recognize that 750 is 30 times 25, so let me write it that way. So when I take the square root of both sides, square root of 4 is 2. Square root of 30 times 30 is 30. And the square root of 5 is 5. Which means S is 30 times 10, which is 300. And BU is the unit that we're using to measure length. Pretty cool. So I think I don't have the book, so I don't have a place where I've got every single problem out of this chapter, but I do think that most of the problems that I have seen, I should say all of the problems I've seen, have been solved either with similar triangles or with the Pythagorean theorem. And they're all right triangles. Okay. Now, I mentioned that the Chinese were advanced in mathematics. They were way ahead of the Babylonians and the Egyptians. They and the Indian civilization, we saw how far along they were. They were pretty far along in algebra, did a lot with numbers. The ancient Chinese, the Chinese knew about the negative numbers as well as the Indians did. They also had a base 10 system that they came up with. It's not clear whether or not they borrowed from each other, how much they influenced each other, just because we don't have that kind of information. All right, but we do know, we have evidence that the ancient Chinese used some very advanced techniques to solve some of their problems. And this next one, they solved using matrices. This is linear algebra. This is so cool. So I'm just going to set it up and then show you in the book what they did. Let's share the screen. Here's the problem. Okay. There are 3 classes of grain, of which 3 bundles of the first class, 2 of the second, and 1 of the third make 39 measures. All right, so each bundle of grain has a certain number of measures in it. And the number of, and first class has more measures than third class. Okay, third class is the lower class. So the first class has more measures than the second class, which has more measures than the first class. We'll see that with our answer at the end. Okay, there are 3 classes of grain. I'm getting tangled up here. Let me write over here. This is the grain problem. And if I let X, let me show you the problem real quick. So the first sentence gives you 1 set of relationships. The second sentence gives you another set, 2 of the first, 3 of the second, 1 of the third makes 34. And the third sentence gives you the third set of relationships, 1 of the first, 2 of the second, 3 of the third. We've got 3 variables. We don't know how many measures there are in a bundle of the first class, in a bundle of the second class, in a bundle of the third class. We've got 3 different relationships, 3 equations, 3 unknowns. It's an algebra problem. Okay, so let's set it up. All right, you probably didn't write all that down, and I can look back and tell us what it is. We're going to let X equal the number of measures in a first class bundle. And Y is the number of measures in a second class bundle. And Z is the number of measures in a third class bundle. Those are our three unknowns. And we're representing them with X, Y, and Z. They didn't have an X, Y, and Z. They were not able to represent it that way. The symbols that they had to work with were the numbers. They had the numerals. All right. So I need three equations. The first one says 3 bundles of the first class. So I've got 3x plus 2 of the second, 2y, plus 1 of the third, so z, equals 39. Second one says 2 of the first, so 2x, 3 of the second, 3y, plus 1 of the third, makes 34. And then I've got 1 of the first, x, plus 2y, plus 3z, equals 26. Those are my 3 equations. Now you might remember from high school when you did solved systems of equations, especially when you only had 2 variables, you would figure out what y was, you would eliminate the x, figure out what y was, and then substitute back in to get x. You would use the substitution method. You might eliminate some stuff. You know, when you did, there were several different methods for solving that. Same methods for solving it if it's 3 variables. It's going to take you longer. It's more tedious. So you might remember from linear algebra how we set this up in a matrix. And we set this up by looking at just the coefficients and the constants on the right side of the equations. We took out the x's, the pluses, the y's, the z's, and the equals. So I've got 3, 2, 1, 39 is the first row of my matrix. Second row is 2, 3, 1, and 34. And then 1, 2, 3, 26. All right, there's my matrix. What you did in linear algebra was try to get zeros here, here, and here, so that you could set up an equation that says this many z's equals this number. Solve it for z. And then get your equation from the second line that just has y's and z's in it. Now you know what z is, figure out what y is. Then move up to the top line. Now you know what z is, now you know what y is, you can figure out what x is. Okay, that's the strategy that we used in linear algebra. And the ancient Chinese did exactly the same thing. The only difference was they took this matrix and they rotated it 90 degrees. So the Chinese matrix said 1, 2, 3, 26 was the first column instead of the last row. 2, 3, 1, 34 is the middle column instead of the middle row. And 3, 2, 1, 39 is my last column. And what they did, I'm going to show you in the book. All right, there are our equations. There is the matrix that they came up with. And then they started using row by row elimination. So then they got a 0 in that top spot on the second row. Then they got a 0 in the top spot on the first row. So you've got 0, 0. Then they got a 0 in the second spot on the second row. Now they're ready to go. Now they know that 36z equals 99. So when they solve the problem, they end up with 1 bundle of the low-grade patty, or they end up with z equals 99 over 36. You know, you don't get whole numbers on this. It doesn't come out that nicely. They got y is 4 1/4, and x was 9 1/4. But I think when you're back then, I mean, look at what we're doing. Look at how advanced this is. So they certainly didn't complain about working with fractions when they're doing all this other stuff. That's probably the easy part for them. Okay. One more quick thing to show you. And all I'm going to do is just say that this is on your Canvas site in Module 9. They also knew the Chinese remainder theorem, and these are congruence equations. This is modern algebra. This is our Math 3163. Carl Friedrich Gauss invented congruence equations in the 1800s, and they're solving problems with them that can be interpreted as congruence equations. And the excuse me, the Chinese remainder theorem is an algorithm for solving problems of this type, and it's one that I've got it set up on the Canvas site so you can look at it. It's not easy to remember. You know, if you don't remember that, if you don't use this a lot, it's really easy to forget. It's kind of easy to use. It's just pretty amazing that this is as old as it was. Now, this was not in the 9 chapters on the mathematical art. This was from another book, Master Sun's Mathematical Manual. And remember, I mean, this is a civilization that lasts thousands of years. So it's not like the 9 chapters was the only book, and that was the only mathematician. There were a lot of them. It's just that the 9 chapters has so many problems in one place. And so I would like for you to take a minute when you get a chance, look at that method of the Chinese remainder theorem. I think that's kind of neat. And also this problem, I've got it solved. It shows you how to set it up with congruence equations, and then shows you what the theorem is. Shows you how to use that theorem. Okay. All right. I'm going to stop there. It's time to go. And so next Tuesday, we don't have class. So you're going to be on your own for the next 2 weeks, looking at what's on our Canvas site, and I'll send you some messages telling you what you need to be working on. But I do want you to make sure that over the break, you take a break and, you know, stay away from history of math unless you just absolutely can't stand to be away. And, you know, if doing the homework is your hobby, then, and that's how
truly my favorite pastime.
Isn't it? Me too. You know,
I'm gonna binge watch all the previous lectures.
yeah, right. Sweet of you to say so.
Show it to my girlfriend because it's so interesting, right?
Oh, that'll do it. That'll seal the deal, I'm sure.
Yeah.
All right. Y'all be good and have a wonderful week and a great
Thank you.
weekend.
You as well.
And you be really careful. Use your seat belts. You know, wear those masks. Take care. Bye-bye.
Bye-bye.